So in this video, we're going to derive the multivariable chain rule. So here's the situation. If you have z as a function of x and y, and then each of x and y are a function of t, then we would like to find the rate of change of z with respect to t. So this reminds us of the chain rule, or a situation in which we'd use it. We have z depending on some variables, which in turn depend on another variable. Can we figure out how z depends on that last variable? So if you think back to Math 126, you had, we talked about a tangent plane or a linearization, and basically we had a surface, let's see, some surface. Let's try to make this look three-dimensional. And then if you found a point on the surface, we could attach a plane to that point. And as long as you stay pretty close, that plane was a good approximation of the surface. And that was the point of the linearization. And here was the formula. If that point was x naught, y naught, z naught, then it's basically a glorified point slope form, right? Which I'm not a huge fan of point slope form, but it does work. So we have those three, and then we took the partial derivatives, and those were a good approximation of how the function was changing if you walked in the x direction and the y direction. And then especially if we made x naught, y naught, z naught really close to x, y, and z, this was a great approximation. So we could actually write, so maybe for the function, that's approximately equal. But if we made these small, if we made those dz like we do in calculus, then we can actually change that to an equal sign. Dx plus the partial z with respect to y dy. Okay, and then those are the small changes in x, y, and z, and if we just don't really think of it this way, but we're kind of dividing by dt. So we take those small changes over a small period of time. It's not really division. It's not always correct to think of the d's as numbers, but it often does work. Sorry. So you've got to really differentiate between, if anyone actually took 126 with me as a TA, maybe you remember this. I'm picky about the partial d and the normal d because they actually do mean different things, and we have both now. So, sorry, dx by dt. We're not doing anything, we're just dividing by dt, but make sure your partials and your regular, I'm writing this completely wrong, make sure your partials and your regular d's look significantly different. Okay, and this is the three-dimensional chain rule. So that's interesting. This part looks like a chain rule, taking derivative with respect to x and then with respect to t, and this part looks like a chain rule, and actually what ends up happening is you just add them up.